October 9th, 1943. A grass field at Norholm Estate, near Varde, Denmark. Hauptmann Hans-Werner Lerche stood at the edge of a clearing and stared at something that should not exist. A Boeing B-17 Flying Fortress sat intact among the tall trees, its 4 Wright cyclone engines cold, its aluminum skin unmarked by fire or catastrophic damage. The American bomber had landed itself here, wheels up, in a controlled descent that left the airframe whole. Lerche had been called from Rechlin, the Luftwaffe's primary testing facility near Berlin, to evaluate whether this machine could be flown out. He had flown more captured Allied aircraft than perhaps any pilot in the German Air Force. Spitfires, Mustangs, a Lancaster bomber. But this was different. The B-17 represented something the Luftwaffe High Command could not reconcile with observable reality. These aircraft flew through 88mm Flak barrages that should have destroyed them. They absorbed direct hits from shells designed to shatter bombers at 6 miles altitude. They returned to England with holes large enough for a man to crawl through. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German fighter pilots reported emptying 20mm cannon rounds into B-17s without bringing them down. Anti-aircraft crews watched their shells explode against fortress formations, seeing black smoke and debris, confident of kills, only to learn later that most of those bombers had landed safely in England. The aircraft defied fundamental principles of structural engineering and combat damage assessment. Lerche had read the intelligence reports. He had studied gun camera footage, but reading reports and examining a captured specimen were different matters entirely. The B-17 at Norholm had developed propeller pitch failure on one engine during a mission. Unable to maintain speed or altitude with one engine frozen in takeoff position, the pilot had ordered his crew to bail out, then set the heavy bomber down in this field, with precision that suggested years of training. The Luftwaffe had recovered the aircraft undamaged. Now Lerche needed to determine if it could fly again, and more importantly, he needed to understand what made these machines so difficult to destroy. He walked the perimeter of the fortress, noting the construction details visible in daylight. The fuselage was not armoured in any conventional sense. The skin was thin, aluminum, no thicker than on German bombers. The wings showed no obvious reinforcement. The tail section appeared delicate, almost fragile. Nothing about the external structure suggested unusual survivability. Yet crews flying these aircraft were surviving encounters that killed pilots in Heinkels and Dorniers. The contradiction demanded explanation. The German Air Force needed to understand what advantage the Americans possessed, what engineering principle or material science had produced a bomber that absorbed punishment beyond theoretical limits. By autumn of 1943, the air war over Europe had developed into an exchange of industrial violence unprecedented in human history. The United States Army Air Forces committed to daylight precision bombing, sending formations of B-17s and B-24s deep into German-held territory without fighter escort for most of the journey. The bombers flew at altitudes between 20,000 and 25,000 feet, where the thin, cold air at 40 degrees below zero made every mission an endurance test for crews wearing heated suits and oxygen masks. The German defense system had evolved into the most sophisticated anti-aircraft network ever constructed. Flak batteries ringed every strategic target. The 88mm Flugzeugabwehrkanone aircraft defense cannon formed the backbone of this system. The Flak 18 and Flak 36 variants could engage targets at 32,000 feet with remarkable accuracy. Each gun fired a shell weighing 20 pounds, packed with high explosive, and a time fuse set to detonate at predetermined altitude. When the shell exploded, it sent hundreds of jagged steel fragments through a sphere of space roughly 100 feet in diameter. German anti-aircraft doctrine emphasized massed fire. Batteries of 4 to 6 guns would concentrate on a single point in the sky, creating a box barrage through which bomber formations had to fly. The shells burst in patterns, black clouds appearing among the silver bombers like ink splashed on paper. Each burst represented lethal fragments moving at thousands of feet per second. A direct hit from an 88mm shell should have been catastrophic. The explosive force alone was calculated to break a bomber's back, severing the fuselage or tearing away control surfaces. Even near misses sent fragments through aluminum skin with enough energy to disable engines, rupture fuel tanks, kill crewmen. The mathematics of anti-aircraft fire were well understood. German gunners knew the altitude of incoming formations from radar tracking. They knew the speed of B-17s, roughly 170 miles per hour, at bombing altitude. They set fuses to burst shells in the path of the formation. The system worked with mechanical precision. Shells exploded where they were supposed to explode. Fragments struck aircraft, yet the fortresses kept flying. Intelligence reports documented the phenomenon but could not explain it. A B-17 from the 303rd Bomb Group had returned to England with the entire nose section blown away by an 88mm shell. The bombardier had been killed instantly. The navigator's compartment no longer existed as a structural element. Wind shrieked through the torn fuselage at 170 miles per hour. The pilots, separated from the destruction by only a thin bulkhead, somehow maintained control and brought the aircraft home across 200 miles of hostile territory. Another fortress absorbed a direct hit to the bomb bay while doors were open and bomb sight extended. The shell detonated among armed 500-pound bombs. The explosion should have destroyed the aircraft immediately. Instead, the blast vented through the open bay doors. The bombs did not detonate. The aircraft's spine was not broken. The crew flew back to England, landed safely, and the bomber was repaired for additional missions. These were not isolated incidents. They represented a pattern that violated German understanding of how aircraft responded to combat damage. The Luftwaffe's testing establishment at Rechlin existed to resolve exactly this type of technical mystery. Engineers there evaluated captured equipment, identified vulnerabilities, developed countermeasures. When a B-17 fell into German hands intact, the testing protocol was standard. Examine the structure. Measure material thickness. Test component strength. Fly the aircraft to assess handling characteristics. Map vulnerable points for fighter pilots and anti-aircraft crews. But the B-17 resisted simple analysis. The aircraft's survivability seemed disconnected from its physical properties. Hans-Werner Lerche understood this contradiction. He had flown 60 different types of German aircraft. He knew what happened when shells hit bombers: fuel fires, structural failure, uncontrolled descents. The standard progression from damage to destruction followed predictable patterns. The B-17 apparently followed different rules, and German combat effectiveness depended on understanding why. Thousands of gunners were firing thousands of shells at hundreds of bombers. The expenditure of ammunition was staggering. Estimates suggested that destroying a single B-17 required 16,000 rounds of 88mm ammunition in 1944. That figure represented a crisis of efficiency. Germany's resources were finite. If each bomber required that volume of fire to bring down, the defensive system would exhaust its ammunition stocks before the bomber offensive could be stopped. The Luftwaffe had built its bomber force on different principles than the Americans. German bombers like the Heinkel He 111 and Junkers Ju 88 emphasized speed and maneuverability over defensive armament. These aircraft were designed to evade interception through performance rather than absorb damage through structure. The doctrine reflected European geography. German bombers operated over relatively short ranges, often with fighter escort available throughout the mission profile. Defensive guns were present, but not primary. The aircraft were built light, maximizing bomb load and fuel capacity while accepting vulnerability as an operational trade-off. This approach had worked well in the early war years. Against Poland, France, and during the Battle of Britain, German bombers had acceptable loss rates when properly employed. The shift to Eastern Front operations revealed limitations. Soviet anti-aircraft fire proved more intense than expected. German bombers began sustaining damage from ground fire that forced crash landings or write-offs, but losses remained within acceptable parameters. The aircraft were doing what they were designed to do, and when they were hit badly enough, they went down. This was expected behavior. The American approach seemed fundamentally different. The B-17 was slower than German bombers of comparable size. It carried fewer bombs relative to its weight. Range was not exceptional for a four-engine aircraft. What it did carry was guns. 1350 caliber machine guns on the G-model variant. Gunners in power turrets covering every approach angle. The Americans had built a flying weapons platform, a bomber that fought its way to the target and fought its way back. The concept was alien to German thinking but comprehensible as a doctrinal choice. What was not comprehensible was the structural resilience. Lerche had examined the intelligence photographs. He had read the interrogation reports from downed American crews. He had studied the gun camera film from Luftwaffe fighters. The evidence was consistent and disturbing. B-17s absorbed damage that should have destroyed them, continued flying, completed their missions, returned to base. The aircraft seemed to possess some quality beyond material construction, some margin of survival that existing engineering theory could not account for. German engineers at Rechlin had proposed several hypotheses. Perhaps the Americans used different aluminum alloys with superior properties. Perhaps the internal structure incorporated redundancy not visible from outside. Perhaps critical systems were protected by armor that reconnaissance photographs had not revealed. These were testable propositions. A captured aircraft in flyable condition would provide answers. That was why Lerche stood in a Danish field looking at an intact B-17. The bomber represented more than a technical puzzle. It embodied an American approach to warfare that troubled German strategic planners. The United States was building these aircraft in quantities that seemed impossible. Factories in Seattle, California, Texas were producing hundreds of fortresses per month. Each one carried 10 men and thousands of pounds of bombs into German airspace. Each one required massive expenditure of ammunition and fighter sorties to bring down. And when brought down, American industry simply built more. The production capacity appeared limitless. Germany could not match this industrial output. The Reich's factories were operating at maximum capacity, and still the numbers were insufficient. Every resource committed to anti-aircraft defense guns, ammunition, radar equipment, trained crews represented resources not available for the Eastern Front or other theaters. The 88mm guns defending German cities could have been used as anti-tank weapons against Soviet armor. The steel in flak shells could have built U-boats. The mathematics of attrition were unfavorable and worsening. Understanding the B-17's survivability, therefore, had strategic implications. If German fighters and anti-aircraft could be made more effective through better knowledge of vulnerable points, fewer resources would be required per kill. If the aircraft's apparent resilience resulted from some engineering principle that could be applied to German bombers, that knowledge was worth having. If nothing else, test flights would help fighter pilots train against an accurate representation of the aircraft they faced in combat. Every piece of data extracted from the captured fortress had potential value. Lerche completed his external inspection. The aircraft was intact, flyable with proper preparation. The engines would need checking, control surfaces tested, German instruments and radio equipment installed for safety, but the basic machine was sound. Soon he would take this American bomber into German skies and discover whether its legendary toughness was fact or myth. The answer mattered more than the Luftwaffe High Command wanted to admit. The B-17 that Lerche prepared to fly from Denmark to the test facility at Rechlin represented 7 years of American engineering refinement. The first flying fortresses had entered service in 1938. By 1943, the aircraft embodied accumulated lessons from thousands of combat missions. Boeing engineers had not designed the B-17 to absorb punishment. They had designed it to complete missions. The distinction mattered. The bomber's structure was semi-monocoque construction. Load-bearing skin worked in concert with internal framework to distribute stress throughout the airframe. The wings employed truss type, spars rather than solid beams. 2 main spars ran the length of each wing, a forward spar and an aft spar. Each spar consisted of upper and lower chords connected by tubular diagonal members forming N-shaped trusses. This design provided strength without excessive weight. When one structural member failed, others continued carrying load. The wing attached to the fuselage at 8 points 4 main attachments, plus 2 secondary connections on each side. Steel terminal fittings bolted into the aluminum spar cords transferred wing loads to matching fittings on the fuselage center section. The entire assembly was secured with close tolerance bolts and tapered pins. If combat damage severed one attachment point, 7 others remained. If flak destroyed a section of wing skin, the underlying truss structure maintained integrity. The redundancy was not obvious from external inspection. It resided in the internal architecture. Fuel tanks represented another engineering priority invisible to observers. The B-17F model carried 18 rubber fuel cells inside the wings, 9 per side. These Tokyo tanks, as crews called them, added 1,100 gallons of capacity beyond the standard wing tanks. The rubber composition allowed the cells to seal themselves when punctured by small-caliber projectiles or shrapnel fragments. Fuel would leak initially, but the rubber compound expanded when exposed to gasoline, gradually closing small holes. Not all holes, not large tears from cannon shells, but enough small punctures to keep engines running long enough to reach friendly territory. The fuel cells consisted of multiple layers, untreated rubber on the inside, a layer of natural rubber, a layer of synthetic rubber, and a vulcanized outer layer. When aviation fuel contacted the inner untreated rubber, it caused swelling that pressed against the other layers, creating pressure that sealed punctures. The system reduced but did not eliminate fire risk. Vapor buildup in partially drained tanks remained explosive, but partially effective protection exceeded no protection at all. Armor plating protected crew positions where weight permitted. The pilot and co-pilot sat behind armored seats. Steel plates shielded critical equipment in the radio compartment. The ball turret gunner had minimal protection, sacrificing armor for mobility in the confined turret. Flak curtains, laminated plates sewn into canvas, hung in areas where rigid armor could not be installed. These curtains stopped low-velocity shrapnel fragments, but not direct shell hits or cannon rounds. They represented another compromise between protection and weight. The distribution of defensive armament on the G-model variant reflected hard-won tactical lessons. 13 50-caliber Browning machine guns covered every approach angle. The chin turret mounting 2 guns addressed the Luftwaffe's discovery that frontal attacks faced fewer defensive weapons. Twin guns in the dorsal turret, twin guns in the ball turret, twin guns in the tail, plus flexible guns at waist positions and in the nose compartment. The firepower did not make the bomber invulnerable. German fighters still pressed attacks home. But the guns forced attacking aircraft to choose approach angles carefully, to endure return fire during attack runs, to break off early rather than press close. The oxygen system that sustained crews at altitudes above 20,000 feet was low pressure by design, reducing explosion risk if damaged. Electrical systems incorporated redundancy, multiple generators, backup batteries, dual circuits for critical equipment. Hydraulic lines for landing gear and turret operation followed separated paths where possible. These design choices cost weight and complexity. They made maintenance more difficult. They reduced bomb load capacity. American engineers accepted these trade-offs because crew survival enhanced overall operational effectiveness more than maximizing payload. German bomber doctrine had evolved differently. The Heinkel He-111 could carry 2,000 kilograms of bombs at speeds approaching 400 kilometers per hour. The Junkers Ju-88 was faster still and could be configured for dive bombing. These aircraft emphasized offensive capability. Defensive guns were present but limited. Protection consisted of speed, maneuverability, and fighter escort. The philosophy worked when those elements functioned as planned. When fighters were absent, when flak was intense, when mechanical failures prevented evasion, German bombers went down. This was accepted as the cost of maximizing offensive punch. The B-17 sacrificed offensive capacity for survivability. Its bomb load of 4,000 to 6,000 pounds compared poorly to the Lancaster's 14,000 pounds. Its maximum speed of 300 miles per hour was slower than German bombers, but its structure incorporated design principles that allowed damaged aircraft to continue flying. Multiple load paths, redundant systems, self-sealing fuel tanks, distributed armor. These features did not make individual aircraft invulnerable. They shifted probability slightly in favor of crew survival. Across hundreds of missions and thousands of aircraft, those slight probability shifts accumulated into measurably better survival rates. Lerche understood engineering. He recognized quality when he examined it. The B-17 represented competent design executed with industrial precision. American factories were producing these aircraft with standardized components, interchangeable parts, documented procedures. Every bomber emerging from Seattle or California or Texas met the same specifications. Quality control was rigorous. Manufacturing tolerance was tight. The Germans could build excellent aircraft. The Focke-Wulf 190 fighter proved that. But German production emphasized craftsmanship over standardization. Each aircraft required individual fitting and adjustment. Production rates suffered. Maintenance complications increased. The American approach sacrificed elegance for efficiency. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Late October, 1943. Lerche sat in the left seat of the captured B-17, engines idling, preparing for his first flight in the aircraft. The cockpit was spacious compared to German bombers. Instruments were clearly labeled in English. Control layout was logical. The 4 throttle levers fell naturally to hand. Mixture controls, propeller pitch controls, fuel selectors all positioned where a pilot would expect them. American cockpit design reflected operational testing, not theoretical ideal placement. He advanced the throttles. The Wright Cyclone engines responded smoothly. The bomber accelerated down the grass strip at Esbjerg, Denmark, where German ground crews had prepared it for flight. The tail lifted. Airspeed increased past 70 miles per hour, past 80. Lerche eased back on the control column. The Fortress lifted cleanly into the air. Climb rate was adequate for the aircraft's weight. Control response was precise without being twitchy. The bomber flew like a transport stable, forgiving, designed to be flown by pilots of average skill under high-stress conditions. At altitude, Lerche evaluated handling characteristics. The B-17 was not maneuverable by fighter standards. It would not dogfight, but it was not supposed to. Its role required straight and level flight on bomb runs, formation keeping during long missions, predictable behavior when damaged. These requirements shaped its flying qualities. Stability exceeded agility. Lerche flew basic maneuvers, turns, climbs, descents. The aircraft responded as expected. Nothing exceptional, nothing problematic. A solid, professional machine designed by engineers who understood their mission requirements. Then he began stress testing, steep turns, aggressive control inputs, simulated combat maneuvers a desperate pilot might attempt. The airframe handled these without complaint. No excessive vibration, no control flutter, no structural groaning audible over engine noise. The bomber was substantially built, but that alone did not explain its combat survivability. He had flown German bombers that were substantially built. They still went down when hit hard enough. After landing at Rechlin, German engineers began detailed examination. They measured skin thickness throughout the airframe. Standard aluminum alloy, nothing exotic. They examined joint construction, rivet patterns, structural reinforcement locations, competent work, but not revolutionary. They tested material samples, 24 ST aluminum alloy and 24 ST Alclad corrosion-resistant aluminum with pure aluminum cladding. Good materials, properly applied. Nothing Germany could not produce if industrial capacity permitted. The fuel cells were examined with particular interest. German engineers cut sections open to study the layered rubber construction. The self-sealing mechanism was understood in principle, but seeing the actual implementation provided insights. The Americans had refined the design through multiple iterations. Early self-sealing tanks had been less effective. The 1943 production standard represented accumulated improvements. This was engineering as an iterative process: build, test, improve, repeat. Time and resources invested in refinement rather than radical innovation. Ground tests simulated combat damage. Engineers removed sections of wing skin to determine how much structure could be lost before flight characteristics degraded unacceptably. They discovered that substantial portions of wing surface could be missing without immediate catastrophic failure. The underlying truss structure continued supporting load. Flight characteristics suffered reduced lift, increased drag. Asymmetric handling but controlled flight remained possible. A damaged fortress would not be combat effective, but it might reach friendly territory before structural failure occurred. The fuselage structure showed similar resilience. The bomb bay interrupted longitudinal stiffeners that normally ran the length of the fuselage. German engineers expected this break in structure to be a major weakness point. Instead, they found compression struts and truss arrangements that transferred loads around the bomb bay. A direct hit to the bay would still be catastrophic if bombs were aboard, but structural damage to the bay doors or supporting framework would not necessarily doom the aircraft. What German analysis revealed was not a single brilliant innovation, but an accumulation of modest improvements consistently applied. The B-17 did not survive because it had revolutionary armor or exotic materials. It survived because every system incorporated redundancy where weight allowed, because structure distributed loads through multiple paths, because fuel tanks partially sealed themselves, because engines could run longer on damaged systems, because pilots had backup instruments and alternate control paths. The tactical implications troubled Lerche and the intelligence officers who received his reports. The Luftwaffe fighter force was optimized to bring down bombers with minimal ammunition expenditure. Standard doctrine called for head-on attacks using 20mm cannons. 4 or 5 hits would destroy most bombers. But if 20% of hits were absorbed by redundant structure, if another 20% struck non-critical areas, if fuel fires were partially suppressed by self-sealing tanks, then the required number of hits increased. More hits meant more ammunition expended per kill, longer engagement times, greater exposure to defensive fire. Anti-aircraft batteries faced similar mathematics. An 88mm shell hitting a B-17 might destroy it immediately if the hit struck a critical location. But many hits struck non-critical locations. Wings could lose substantial sections and still generate lift. Fuselage could be perforated without immediate structural collapse. Engines could be damaged without immediately losing power. The bomber's design philosophy of distributed systems and redundant structure meant that battle damage was less likely to be immediately fatal. Lerche filed his technical report with Recklin's testing department in November 1943. The document was factual, measured, professional. It contained no personal opinions, only observed data and test results. But the implications were clear to anyone who understood aerial combat mathematics. The B-17 was designed to complete its mission with degraded capability, rather than to avoid being hit. This represented a fundamentally different approach than German bomber design philosophy. The report circulated among Luftwaffe High Command. Fighter pilots read summaries. Anti-aircraft batteries received tactical bulletins based on the findings. The identified vulnerabilities were real engines could be disabled, control systems damaged, crew positions struck, but many of the vulnerabilities required precise hits on small targets from aircraft moving at high speed or from anti-aircraft guns engaging at extreme altitude. The probability of hitting those specific vulnerable points was lower than the probability of hitting the aircraft somewhere, anywhere. And hitting the aircraft somewhere was often insufficient to bring it down. Experienced Luftwaffe pilots confirmed Lerche's findings through combat experience. They reported emptying ammunition into fortresses without seeing them go down. They described bombers trailing smoke, flying with obvious damage, limping away from formations yet still flying. Gun. Camera footage showed hits registering, pieces of aircraft structure breaking away, yet the bombers continued toward their targets. The disconnect between observed damage and aircraft destruction rates contradicted what pilots expected from their training and experience with other aircraft types. The psychological impact on German aircrews was gradual but measurable. Pilots who had confidently engaged bomber formations in early 1943 became more cautious by late 1943. The realization that bringing down a fortress required sustained engagement, multiple attack passes, heavy ammunition expenditure, all while under defensive fire from 13 machine guns made each engagement more daunting. Some pilots pressed attacks home regardless. Others broke off early, conscious that surviving to fight another day had value beyond individual kill counts. Anti-aircraft crews experienced similar doubt. Watching shells burst directly in the path of bomber formations, seeing aircraft shudder from impacts, observing debris falling, yet having formations continue to target and drop their bombs accurately undermined confidence in the defensive system. Gunners increased their rate of fire, fired more shells per target, created denser barrages. This increased kill rates marginally but exhausted ammunition stocks faster. The consumption rate of 16,000 shells per bomber destroyed was unsustainable given production capacity and logistics. The captured B-17 at Rechlin became a training aid. Fighter pilots flew practice attacks against it to identify optimal approach angles and vulnerable points. The exercise provided useful tactical information, but also reinforced the sobering reality that destroying these aircraft required skill, ammunition, and luck. The bomber sitting on the ground, unarmed, unpowered, was simply a large aluminum structure. The same bomber at altitude, in formation with dozens of others, defended by machine guns and escorted by fighters, was an entirely different proposition. Lerche flew the captured fortress several more times through winter 1943 and into 1944. Each flight reinforced his initial assessment. The aircraft was not exceptional in any single characteristic. It was exceptional in its consistent competence across all characteristics. It did nothing brilliantly but everything adequately. For a bomber operating in hostile airspace, adequate performance across all systems, with redundancy for critical functions, was more valuable than excellent performance in one area with vulnerabilities elsewhere. The Americans were not building better aircraft through superior individual technology. They were building better operational systems through superior integration of existing technology. The self-sealing fuel tanks were not American inventions, they had been developed before the war. The truss-type wing spar was not revolutionary. It was basic structural engineering. The distributed armor placement, the redundant control systems, the standardized maintenance procedures, none of these were individually brilliant. Together, consistently applied across 12,000 aircraft, they created a bomber force that was grinding down German defensive capacity through simple attrition. German intelligence tracked American production numbers with growing concern. Boeing alone was producing 300 fortresses per month by mid-1943. Douglas and Lockheed Vega added hundreds more. The Americans were building bombers faster than the Luftwaffe could destroy them. Each fortress shot down was replaced within days. Each German fighter lost took weeks to replace, and the pilot took months or years to replace if he could be replaced at all. The mathematics favored the side with greater industrial capacity, and that side was emphatically not Germany. Lerche never recorded his personal feelings about these discoveries. His memoir, written decades after the war, focused on technical details and flying experiences rather than psychological reflection. But other test pilots and intelligence officers left records indicating awareness that the tide had shifted irreversibly by late 1943. The Luftwaffe could still fight effectively. Individual pilots could still achieve victories. But the strategic situation was deteriorating. The Americans had built an aircraft that matched their industrial and operational philosophy good enough in all aspects, produced in overwhelming numbers, operated by adequately trained crews who could be replaced when lost. Against that system, German technical sophistication and pilot skill were insufficient advantages. The captured B-17 at Rechlin eventually was coded a 3+GE and transferred to Kampfgeschwader 200 for operational missions. It flew supply drops, agent insertions, long-range reconnaissance roles that exploited its range and payload capacity. The irony was not lost on German crews. They were using an American bomber because their own bomber force lacked aircraft with sufficient capability for these specialized missions. The Flying Fortress, designed to bomb Germany, was instead being used by Germany because it was the best available tool for certain jobs. That fact alone testified to the aircraft's fundamental competence. Hans-Werner Lerche flew his last operational mission on April 23, 1945. 15 days before the war in Europe ended, he piloted a Dornier Do 335 from Rechlin to the factory at Oberpfaffenhofen near Munich. The Do 335 was one of the fastest piston-engine aircraft ever built, capable of speeds exceeding 400 miles per hour. It represented German engineering at its most sophisticated. It also represented the futility of technological excellence deployed too late against overwhelming material superiority. Throughout his career, Lerche never crashed or seriously damaged any aircraft he flew. He tested over 125 different types: German, American, British, Soviet. This record testified to exceptional skill, careful judgment, and considerable luck. He survived the war, which was itself an achievement given the casualty rates among Luftwaffe personnel by 1945. After the war, he wrote his memoir, published in 1977 in German and translated to English in 1980. The book focused on technical details and flying experiences. It avoided politics, blame, or self-justification. It was the account of a professional pilot doing a difficult job in extraordinary circumstances. The captured B-17s at Rechlin served various purposes through the end of the war. Some were used for technical evaluation. Others were transferred to Kampfgeschwader 200 for operational missions, supply drops to isolated units, agent insertions behind Soviet lines, long-range reconnaissance where German aircraft lacked sufficient range. The irony was unmistakable. Germany was using American bombers because German industry had not produced equivalent aircraft. The B-17, designed to destroy German industrial capacity, was instead being employed by Germany because it was the best available tool for specialized missions. Most of the captured fortresses were eventually destroyed. Some were lost in combat operations, others were damaged beyond repair and cannibalized for parts. A few were abandoned at airfields as Allied forces advanced. One B-17, Miss Nonnally II, which Lerche had flown from Denmark, and was assigned to Kampfgeschwader 200, but crashed near Bad Vöslau during a transfer flight to Vienna in August 1944. The wreckage was transported to Wiener Neustadt for repair. The repair was never completed. Soviet troops arrived in March or April 1945 and found the partially reconstructed bomber sitting in a hangar. For American crews flying the actual combat missions that these captured aircraft were meant to help counter, the survival statistics told a sobering story. In late 1943, the average operational life of a B-17 was 11 missions. The crews had similar life expectancies. Bomber crews faced higher casualty rates than any other branch of the American military. The 8th Air Force lost 26,000 men killed more than the entire United States Marine Corps, despite the Marines having enrolled 250,000 more personnel. The mathematics of survival were brutal. In 1942 and early 1943, when bomber crews flew 25 mission tours, only 35% survived to complete their tours. The probability of death or capture was roughly 2 in 3. Later, when fighter escort became available and the Luftwaffe's strength declined, survival rates improved. By 1944, 66% completed 25 to 30 missions. By 1945, 81% finished 35 mission tours. But those improved rates came after the period when German analysis of the B-17 was most relevant. The 8th Air Force flew over 226,000 B-17 sorties during the war. They lost 4,228 fortresses in combat, roughly 1 in 50 sorties resulted in an aircraft loss. But aircraft could be replaced. 12,731 B-17s were built during the war. Production outpaced losses by a substantial margin. Crews were harder to replace. Each bomber carried 10 men. Training a complete crew required months and significant resources, but American training capacity was sufficient to sustain the losses. The industrial and demographic advantages that allowed mass production of aircraft also allowed mass production of trained personnel. German defenders faced the inverse problem. They could destroy American bombers, but not fast enough to prevent strategic damage. They could kill American crews, but replacements kept arriving. Meanwhile, German fighter pilot losses could not be adequately replaced. By late 1944, the Luftwaffe was flying pilots with minimal training against increasingly experienced American crews, supported by long-range fighter escorts. The technical insights gained from captured B-17s provided tactical advantages but could not overcome strategic disadvantages in production capacity and pilot training. The broader lesson that Lerche's testing revealed was that American military aviation had embraced a fundamentally different philosophy than German aviation. The Germans built excellent individual aircraft, the Focke-Wulf 190 fighter, the Messerschmitt 262 jet, the various experimental designs that Rechlin evaluated. These aircraft often outperformed their Allied counterparts in specific parameters, but they were built in insufficient numbers, maintained with difficulty due to non-standardized parts, and operated by pilots whose training suffered from fuel shortages and compressed timelines. The Americans built good enough aircraft in overwhelming numbers. The B-17 was not the best heavy bomber of the war by many technical measures. The British Lancaster carried more bombs. German jets were faster. But the Fortress was reliable, maintainable, producible, and survivable enough to accomplish its mission when employed in large formations with adequate support. That combination of adequacy and availability proved more valuable than technical excellence deployed in limited quantities. The intelligence gathered from captured B-17s influenced German tactical doctrine but could not alter strategic reality. Fighter pilots learned optimal attack angles and vulnerable points. They developed tactics specifically for engaging fortress formations. Anti-aircraft batteries adjusted their firing patterns based on observed damage effects. These adaptations increased effectiveness marginally, but margins were insufficient when facing a force that could absorb losses and continue operations. The fundamental problem German defenders faced was not lack of knowledge about how to destroy B-17s. The problem was insufficient resources to destroy them in adequate numbers. Every factor worked against German defensive efficiency. The bombers flew in combat box formations, where defensive fire from multiple aircraft overlapped. Fighter attacks from any angle faced return fire from dozens of 50 caliber machine guns. Anti-aircraft shells had to be fused precisely to detonate at altitude in the path of the formation. Even when shells exploded correctly, the distributed structure and redundant systems of the fortress often absorbed damage without immediate catastrophic failure. The consumption rates were unsustainable. 16,000 rounds of 88mm ammunition per bomber destroyed. Those were estimates for 1944, when defensive systems were most refined. Earlier in the war, when doctrine and equipment were less optimized, the consumption was higher. Germany's ammunition production could not sustain those expenditure rates across all fronts. Every shell fired at Allied bombers was a shell not available for anti-tank defense on the Eastern Front or for coastal defense against invasion. The same calculation applied to fighters. Luftwaffe pilots developed effective tactics against B-17s, head-on attacks from above, where defensive armament was lighter, concentrated attacks by entire squadrons overwhelming local defenses, use of rockets and heavy cannon to destroy bombers beyond effective range of defensive guns. These tactics worked when conditions allowed their execution, but executing them required fuel for training, fuel for operations, ammunition for weapons, replacement aircraft for losses, and replacement pilots when veterans were killed. By mid-1944, all these factors were in short supply. American fighter escorts made massed attacks costly. Allied bombing of German refineries reduced fuel availability. Loss rates among experienced pilots could not be replaced by accelerated training programs. The Luftwaffe was being ground down by attrition warfare, where the side with deeper reserves inevitably won. Understanding the B-17's vulnerabilities did not change these fundamental realities. The strategic bombing campaign that the B-17 enabled was itself debatable in effectiveness. Post-war analysis suggested that the damage to German industrial capacity was significant but not decisive until 1944. German production actually increased through 1943 despite bombing. The campaign did force Germany to divert enormous resources to air defense resources that could have been used elsewhere. Flak guns that defended factories could have been used as anti-tank weapons. Fighter aircraft defending Germany could have supported ground operations. The tens of thousands of personnel manning air defenses were not available for frontline combat. Whether the strategic bombing campaign was worth its cost in Allied lives and resources remains historically debated. What is not debatable is that the campaign was conducted with heavy bombers built to survive damage, crewed by men who understood their survival depended on formation, discipline, and mutual support, and sustained by industrial capacity that could replace losses faster than they occurred. The B-17 embodied this approach. It was not invulnerable. It simply had to be vulnerable enough that acceptable numbers survived each mission. Lerche's technical reports documented this reality with engineering precision. The bomber could absorb substantial damage because its design incorporated redundancy and its structure distributed loads through multiple paths. Individual hits often failed to achieve catastrophic results because critical systems were duplicated or protected. The aircraft's survivability was not mysterious or magical. It was the predictable result of design choices that prioritized crew survival and mission completion over maximum performance or payload. For German strategic planners, this knowledge was both useful and deeply troubling. It was useful because it allowed more efficient targeting of the aircraft's actual vulnerabilities. It was troubling because it revealed that American engineering philosophy was aligned with American strategic advantages. The United States could afford to build aircraft with redundant systems, self-sealing fuel tanks, distributed armor, and excess structural strength. These features added weight, reduced performance, and increased manufacturing complexity. But American industry had the capacity to build such aircraft in quantity. German industry, operating under resource constraints and Allied bombing, could not match that production even when building simpler designs. The captured fortresses at Rechlin ultimately served as evidence of an uncomfortable truth. Technical analysis could identify how the aircraft worked and how to destroy it more efficiently, but efficiency gains in destruction could not compensate for the disparity in production rates. America was building bombers faster than Germany could shoot them down, while training crews faster than Germany could kill them, while producing fighters faster than Germany could match them. The strategic initiative had shifted irreversibly by 1943. The captured B-17s helped German defenders fight more effectively. They did not help Germany win the war. The B-17 Flying Fortress became iconic not because it was the best bomber of World War II, but because it represented American industrial might and operational philosophy translated into aluminum and rivets. The aircraft's reputation for toughness was earned through thousands of PERSD missions where damaged bombers limped home with dead engines, torn control surfaces, wounded crews, and massive structural damage. These survival stories accumulated into legend, but the legend obscured an important reality. The fortress did not survive because it was magical. It survived because Boeing engineers had designed it with redundancy, because American factories could afford to build in that redundancy, because military doctrine emphasized crew survival as force multiplier, and because industrial capacity allowed acceptable loss rates while still overwhelming defenses through mass. The aircraft was a system within a larger system. Its effectiveness depended not just on its design but on the industrial, logistical, and operational infrastructure that sustained it. Hans-Werner Lerche's testing revealed these principles to German intelligence. The revelations did not alter the outcome of the war. By October 1943, when Lerche first flew a captured fortress, The strategic balance had already shifted beyond recovery for Germany. The lessons learned from the B-17 could improve German tactical effectiveness. They could not overcome American strategic advantages in production, resources, and replacement capacity. The broader historical lesson extends beyond the specific aircraft. Military effectiveness in industrial warfare depends not on individual weapon superiority, but on integrated systems of production, logistics, training, and operational doctrine. An excellent weapon produced in small quantities and operated under resource constraints will lose to an adequate weapon produced in overwhelming quantities and operated with sufficient support. The Germans built many excellent individual weapons during World War II. They lost the war because excellence in design could not compensate for inadequacy in production capacity. The B-17 embodied the opposite approach. It was good enough in all critical parameters. It incorporated design, features that enhanced survivability at the cost of performance and complexity. It was built in enormous quantities by an industrial system optimized for mass production. It was operated by crews who received adequate training and could be replaced when lost. It was supported by a logistics system that provided fuel, ammunition, spare parts, and maintenance across thousands of miles of ocean. This integrated approach proved more effective than German technological sophistication because it aligned design philosophy with industrial capacity and strategic requirements. The Americans did not need the best bomber. They needed a bomber that could be built in quantity, maintained in the field, survived damage often enough to complete missions, and was acceptable to crews who had to fly it into hostile airspace. The B-17 met those requirements. That was sufficient. For Luftwaffe pilots and anti-aircraft crews facing formations of flying fortresses in 1943 and 1944, the aircraft's resilience seemed almost supernatural. They hit it repeatedly with weapons designed to destroy bombers. Often it kept flying. Sometimes it completed its mission despite catastrophic damage. The survivors returned to England, were repaired, and came back days later. The psychological impact of fighting an enemy who absorbed such punishment and continued operating was substantial. But there was nothing supernatural about the B-17's survival characteristics. Lerche's testing had documented the engineering principles that enabled that survival: self-sealing fuel tanks that partially closed small punctures, redundant control systems that allowed continued flight with major damage, distributed structure that transferred loads through multiple paths when individual members failed, armor placement that protected critical crew positions and equipment. These were deliberate design choices based on operational requirements and industrial capability. The captured B-17s at Rechlin demonstrated that American engineering had achieved competent implementation of known principles. German engineers could understand the design. They could replicate individual features. What they could not replicate was the industrial system that produced 12,731 of these aircraft during the war, while simultaneously building tens of thousands of fighters, transports, and other types. The disparity in production capacity was the decisive factor, not the quality of individual designs. When Lerche stood in that Danish field in October 1943 looking at an intact flying fortress, he was examining a symbol of American industrial power. The bomber itself was impressive but not revolutionary. What was revolutionary was the system that could build such aircraft in overwhelming numbers, crew them with adequately trained personnel, operate them despite heavy losses, and sustain that effort across years of combat. German technical analysis could identify the bomber's strengths and weaknesses. It could not overcome the strategic reality those strengths and weaknesses represented. The 5 minutes that began at 10:24 in the morning on June 4, 1942 at Midway had demonstrated Japanese vulnerability to American industrial capacity. The months of analysis that began in October 1943 when Lerche flew captured fortresses demonstrated German vulnerability to the same industrial capacity expressed through different weapons. The pattern was consistent. America's advantages lay not in technical superiority, but in production volume, logistical depth, and the ability to absorb losses while maintaining operational effectiveness. The B-17 Flying Fortress earned its place in history, not by being invincible, but by being survivable enough, producible enough, and effective enough when employed in mass. That combination defeated German air defences, not through technical brilliance but through relentless accumulation of modest advantages consistently applied. The captured aircraft at Rechlin taught German engineers how the bomber worked. History taught a larger lesson about how industrial warfare worked. The side with greater production capacity, deployed with competent engineering and adequate operational doctrine, would prevail regardless of enemy technical sophistication. Hans-Werner Lerche survived the war, wrote his memoir, and lived to see the Dornier d'Eau 335 he flew on his last mission displayed in a museum. The flying fortresses he tested were scrapped, destroyed, or abandoned. But the principles they embodied, redundancy, survivability, mass production, became fundamental to post-war military aviation. The lesson was learned. In industrial warfare, good enough in overwhelming quantity defeats excellent in limited numbers. The captured B-17s at Rechlin proved that lesson conclusively to anyone willing to understand its implications. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.